Welcome. We often hear that computer vision is about teaching computers to see. While true, that's like saying civil engineering is about stacking bricks. For us, as engineers, scientists, and architects, the real story is far more interesting. It's about designing resilient systems that can interpret visual data reliably under chaotic, real-world conditions. It's about managing data pipelines at scale, making critical architectural trade-offs, and understanding the failure modes of models that might be controlling a vehicle or diagnosing a disease. Over the next few minutes, we're not just going to define computer vision. We're going to dissect its modern anatomy and explore the hard-earned wisdom needed to build production-ready systems. Every mature computer vision system, whether it's in a Tesla or on Instagram, follows a core pipeline. It begins with acquisition and pre-processing. This isn't just about loading an image. It's our first line of defense against domain shift. Think about standardizing lighting, augmenting data to simulate rain or fog, or resizing inputs for a specific architecture. Next, feature extraction. We've moved from handcrafted features like SIFT and HOG, which were brilliant but brittle, to learned representations via deep learning. A ResNet, for example, isn't just a model, it's a powerful automated feature extractor. Finally, the inference and post-processing stage. Here, the model makes its prediction, but our job isn't done. We might apply non-maximum suppression in object detection to clean up bounding boxes, or translate a segmentation mask into actionable data for a robotic arm. Each stage is a point of potential failure and a lever for optimization.
Let's talk architecture. For years, convolutional neural networks, or CNNs, were undisputed kings. Their power comes from a brilliant inductive bias, the idea that pixels are spatially related. A convolution is a local operation that respects this structure, making CNNs incredibly data efficient and powerful for tasks like classification and detection. Then came vision transformers, or VITEs. They challenge that core assumption. A VITE slices an image into patches, flattens them, and treats them like words in a sentence. It uses a self-attention mechanism to learn the relationships between all patches, regardless of their position. The trade-off? Transformers are data-hungry and computationally expensive, but at massive scale, they can outperform CNNs by learning more global relationships. Choosing between them isn't about which is better. It's a design decision based on your dataset size, compute budget, and the specific problem you're solving.
A model with 99% accuracy on a Kaggle dataset can fail catastrophically in production. Why? The real world is messy. The biggest monster is domain shift. Your model, trained on pristine online images, now has to work with blurry, low-light phone pictures. This is where robust data augmentation and domain adaptation techniques become critical. Another challenge is adversarial robustness. It's been proven that imperceptible changes to an image can trick a model into making a completely wrong prediction. This isn't just an academic problem, it's a security vulnerability. Finally, there's inference optimization. Your state-of-the-art billion-parameter model needs to run on an edge device with limited power. This is where MLOps comes in, using techniques like quantization, pruning, and knowledge distillation to create smaller, faster models without catastrophic drops in accuracy. These are the problems that separate hobby projects from industrial-grade AI systems. So, where are we heading? The future of vision is about moving from understanding to creating. Generative models like DALL-E 3 and Midjourney are a prime example, turning text into photorealistic images. This fusion of language and vision is a key trend. Another frontier is 3D vision. Technologies like NeRFs, neural radiance fields, are allowing us to create stunning, navigable 3D scenes from a handful of 2D pictures. This has enormous implications for AR, VR, and robotics. But the ultimate goal is multimodality. Future systems won't just see. They will see, read, listen, and reason holistically. As practitioners, our greatest opportunity is to stop thinking of computer vision as a standalone field. Instead, we must architect it as a critical sense within a much larger integrated intelligent system. That is the challenge and the opportunity ahead.